All right, last problem in this chapter, and it's a good one. We've got an oil pump that is drawing 44 kilowatts of electric power while pumping oil that has that density at that rate. The inlet and outlet diameters are 8 centimeters and 12 centimeters respectively. If the pressure rise in the oil in the pump is measured to be 500 kPa, the motor efficiency. All right, this efficiency is 0.9. I'll determine the mechanical efficiency of the pump. Okay, this is a good one. Now, it's not explicitly stated, but it's assumed that this is still pumping out the same amount of fluid as it's pumping in. If it wasn't, then fluid would be collecting in the pump, and we know that a pump, just whatever comes in, it's going to go out. There's no reservoir for it to collect fluid. So it's pumping with the same volumetric flow rate in and out, also the same mass flow rate in and out, and we're assuming this is a constant density oil. All right. So first things first, do you see this right here? It's drawing 44 kilowatts of electric current of power, but it's only 90% efficient. So how much shaft power or shaft work is really going to our pump? Let's do that real quick. The shaft work that's actually getting out of the 90% efficient motor would be 44 kilowatts times 0.9 would be 39.6 kilowatts. Okay, so we'll only have 39.6 kilowatts that is, now going out of the motor, which is the work into our pump. We're probably going to need to know that if we want the mechanical efficiency. The mechanical efficiency of the pump would be the work that's actually happening over the work in from the shaft, and that's the 39.6. All right, so we've got 39.6. So now we need to find the actual work that is being done. What type of change in energy is actually happening? I don't see any change in potential energy. It doesn't tell us anything about a low height to a high height. This probably isn't a very large pump right here. It doesn't give us any vertical dimension or anything. What does it give us, though? That change in pressure, that's a big one. Change in pressure. So there is some flow work. We don't really say delta flow work, but there is some flow work because of the change in pressure. Anytime you see a change in pressure at a pump, then we've got flow work. And I don't know if you see this, but if we have an amount of fluid coming into an 8 centimeter diameter pipe and the same amount of fluid going out of a 12 centimeter diameter pipe, there is a change in the velocity. It doesn't tell us the velocity going in and the velocity going out, but I think we have enough information to find the velocity going in and enough information to find the velocity going out. And so there are two things here of actual work or actual changes in energy that's actually happening that the pump is doing. All right, let's try to figure this out. Can we figure out the velocity at the inlet if we know the volume at the inlet and the size of the inlet? Now I could really kind of just do a little figuring out these units to help me out here. But an equation that would be helpful to have on our formula sheet is that the volumetric flow rate is velocity times area. The volumetric flow rate is velocity times area. Let's think about the units, make sure that makes sense. A velocity of like meters per second, an area of meters squared. Yeah, I think that makes sense. That that would give us the volumetric meters cubed per second flow rate. So at the inlet, at the inlet equals VA. Let's write it over here. I know that the volumetric flow rate is 0.1 meters cubed per second. That's going to be equal to the velocity that I'm trying to find times the area. Pi by 4. Diameter is 8 centimeters. Let's say 0.08 meters squared. Pi by 4 diameter squared. Right. Solve that for V1 is 19.9 meters per second. V1 is 19.9 meters per second, whereas V2 is same volumetric flow rate, would be V2 times its pi by 4.12 squared. V2 would be 8.84 meters per second. 8.84 meters per second. So we're actually losing velocity. That's kind of a negative work or a negative change in energy, but that's fine. We probably have a positive change in energy due to the flow work. All right, so now I think we're ready. The work that is actually happening would be a change in kinetic energy and a let's not say change, but and a flow work. We'll put a dot over it because these are powers. These are watts or kilowatts. So the work would be 1/2 m dot v2 squared minus v1 squared plus p2 minus p1 v dot. So those equations would be on our formula sheet. The kinetic energy, normally I think of kinetic energy as 1/2 mv squared, but that's the total kinetic energy. The power kinetic energy is 1/2 m dot v squared. Also with flow work, the total flow work is delta P times V, the volume, but for this power, it's delta P times V dot. Delta P times V dot. All right. So here we go. Kind of like the last problem. I wasn't given m dot. This is V dot. That is V dot. Right, that is V dot, but how do we get m dot? M dot is rho V dot, and they just told us the rho in the problem statement. 860 kilograms per meter cubed times the V dot, 0.1 meters cubed per second, and V2 is 8.84 meters per second squared minus 19.9 squared. That is the work, or the change. That's the change in kinetic energy. That's the change in kinetic energy. All right. That, if I kind of took a break here and multiplied this through, I haven't done the flow work just yet, but that is going to be 13,668 watts. Okay. If we're just in the usual kilogram, meters per second squared, meters cubed, that's just going to be in watts. It's going to be a large number. So I'm going to change it to kilowatts, 13.668 kilowatts. All right. And that is negative. That's a big thing. That is negative, right? If we are slowing a fluid down, which is what it's doing, the fluid is going out slower than it is going in, it has a negative change in kinetic energy, right? Right. This was larger than that. My calculator gave me negative 13,668, so negative 13.668 kilowatts. All right, but then the flow work, the change in flow work would be 500 kPa. 500 kPa. Y'all know that joke with Newton and Einstein and Pascal. A kPa is a kilonewton per meter squared. All right, a kPa is a kilonewton per meter squared, which would give me kilowatts. If I want my units to be, we could say 500,000 newtons per meter squared is my change in pressure times the V dot, 0.1 meters cubed per second. So this would give me 50 or 50,000 watts or 50 kilowatts. All right, so a positive 50 and negative 13. The total work, add those together. The work actual, the power actual, 36.3 kilowatts. Let's step back and make sure that makes sense. The motor is getting 44, it's delivering 39, and the actual work that's happening is really just 36.3. Yeah, I think that makes sense. You know, we're not going to get 100% of the work out than the work that we get put in because of the inefficiency of the motor and because of frictional effects, mechanical efficiency of the pump. All right, so it's asking for, let's answer the question. Mechanical efficiency of the pump, the 36.3 over 39.6. The efficiency of the pump, 36.3 over 39.6, 0.918 or 91.8% is the mechanical efficiency of the pump. Now this one didn't ask for it, but the overall efficiency would be the efficiency of the motor times the efficiency of the pump would be 82.6. Another way to find this overall efficiency would be 36.3 over the complete 44. Let me just, before I tell you, which would be also the 82.6%. All right, the question didn't ask for that, so let's don't get into a habit of answering things that it doesn't ask for. But many times it might ask for the overall efficiency of the pump. All right, let's take a step back and look at what we did. That was a good one. That is a test type problem. So first things first, if you're given the draw of the motor and the efficiency of the motor, go ahead and do a quick multiplication to figure out the work that's going out of the motor into the pump. And then think about, all right, is there a change in potential energy? Is there a change in kinetic energy? Is there some change in pressure? To think about what all types of energy is really changing. This one was a little bit tough to see that change of kinetic energy. We got the kinetic energy change from getting the velocities, and then 1/2 m dot v squared and delta p v squared as our actual work that is happening. And it's okay that one was positive, one was negative. That's okay. And we finally got the actual work over how much it's getting from the motor to get the mechanical efficiency. Here's my final answer. 91.8% is the efficiency, the mechanical efficiency of just the pump. Just the pump.